Welcome to Hot Chips 22. Keynote 2. Looking at transportation in new ways. What does mobility look like in the future?
I'd like to welcome you back from lunch. I hope you had a nice time out in the hot Silicon Valley sun. I'd like to introduce our second keynote speaker, Dr. Burkhard Huhnke. Dr. Huhnke was born in Braunschweig in Germany in 1967, and he actually went to school in Braunschweig as well. They have a great technical university, and I know Intel is working with that school in close collaboration as well. He then joined Volkswagen after several stages in his career about 10 years ago. And the connection with Volkswagen also brought him to Silicon Valley, as Volkswagen was looking to establish a research center to tap into the semiconductor and electronics industries in Silicon Valley. And Dr. Huhnke currently leads the Volkswagen Research Center over here. We've had a keynote from Stanford University, Sebastian Thrun here a year or two years back on self-driving cars. Sebastian's team works with Dr. Huhnke's team over here on the industry side. And so Dr. Huhnke will cover the latest in self-driving cars. But Dr. Huhnke will also talk about really new ways of looking at mobility. He will cover electronics in cars in general. He will look at safety systems and the advances in safety systems in electronics in cars. He will look at communication systems to better manage traffic flows. He will tell us about entertainment. And he will tell us about, and this is the latest fields of electronics in cars, about battery-powered vehicles and driven by the need to get away from oil into renewables. And so he will touch on battery technology and battery-powered vehicles as well. With that, I'd like to introduce Dr. Huhnke.
Yeah, Ralph, thank you very much for the introduction. It's really a pleasure to be here. Thank you very much for the introduction and specifically for the invitation and the chance to talk to you. I separated the speech into 5 parts. I'd like to talk about the Silicon Valley a little bit, and then 4 topics, technical topics: driver assistance, human-machine interface, e-mobility, and the connected car. Looking into transportation into new ways. Why in the Silicon Valley as a conservative car manufacturer? Of course, we are interested in the idea-generating process here in the Silicon Valley. And as you can see, the global research and development program of Volkswagen allows us actually to work in the specific areas of the world in a global perspective and bring all the best of each culture, of each society, and of each technology together. So we are here in the Silicon Valley within this worldwide collaboration knowledge network, teamwork of experts worldwide. We are driving these innovations, and that means we are building up comparison concept cars to compare them. It's a kind of internal contest and best solutions in cars for the customer. The EL is a bridge. What do you mean with that? As you know, you're experts of the Silicon Valley. Silicon Valley engineering means out-of-the-box thinking. It means rapid evolution of ideas and make do with minimal resources, startup companies, and borrow technology from other fields, learn from other fields, and how can we make this work as soon as possible? That's the question. Automotive engineering, that's more the label of conservative mechanical engineering, focus on safety and manufacturability, a century of in-vehicle experience, crash test and validation resources, trust this automotive technology, and prove that it works in all situations. So bring that together, and make really something fascinating out of that. That's our vision here, technology to the people, and we mean That's an environment which really generates ideas. Ideas generates real products. And that's what we are participating here in the Silicon Valley. New bold ideas and technology meeting automotive requirements. Let me briefly introduce the topics at the Electronics Research Lab here in Palo Alto. We work on the driver assistance systems, on connected car, on the human-machine interface, and e-mobility development. What are the challenges of the society? What are the global challenges of today? Of course, we need to talk about the CO2 reduction. We need to talk about fossil fuels, and we need to talk about alternative drivetrains for the future. What else is necessary to think about that? We are going to go into the urban millennium. We are going to talk about at least 20 cities worldwide with more than 10 million people living in these areas. That means we have a lack of space. And of course, it's independent. If you look into Los Angeles or Dakar, poor or rich both have to wait. So traffic jam, everyone is familiar with that. But do we have solutions to resolve these problems? Eventually together, and that's the first invitation I'd like to do today, let's think about these problems together. It doesn't make sense to create centers of expertise just from one field of technology. Let's do that together. That was one of the reasons why we recently founded and officially inaugurated by the German Chancellor the Volkswagen Automotive Innovation Lab here at Stanford at the campus. And I will come back to that point later. So the challenges for the society are decreasing energy resources at a rising cost, increasingly complex traffic situations, and increasing need for safety. How can we cluster these problems to identify problem solutions as soon as possible? Of course, we can cluster them into mobility, society, energy, and safety. For instance, we have increasing vehicle numbers. At the same time, we have a climate change, and we need to look into the CO2 reduction. But of course, we need to keep up the mobility high to reach our working areas, to reach our vacation areas, wherever. So mobility is definitely increasing and growing continuously, but the cost for the traffic and mobility is also increasing as well. The quality of traveling is getting higher and better because we have all these services, information available coming from the internet, for instance, which can be combined. And one interesting aspect, also the society is continuously changing. In 1992, we had approximately 15 segments of different cars, and we were talking about an equation between driving pleasure, price, prestige, and use and variety. Today, we have more than 40 segments. So that's a huge challenge, of course, also for a car manufacturer like us to identify niche products also and to create the right solutions for these products. Electronics is a very important part in this equation. Electronics enables new functions but requires a novel interpretation of usability. It's not possible just to integrate, let's say, a Google Map viewer into the car without thinking about the right human-machine interface. It's not possible to start letting the car driving autonomously over the highway without thinking about rules, laws, liability. But it's of course very interesting to think about the opportunity and bring all these interesting circumstances and conditions into the right order to be ready for driving into the 21st century. Maybe you remember this little thing here, which is one of our very important historical product, of course, and it was very simple technology. It was really very simple. Meanwhile, and this is just the gearbox CPU, we represent there the length of the software code on these pictures. If you compare this to 1980, the complexity of these little devices have increased dramatically. And we don't have just one of these CPUs in our cars, we have almost 50. So how can the automobile of the future look like? We think the car needs to learn to see, a vision technology to understand the environment, to make the right decision. The car is connected, wireless mobile communication in a smart way. That doesn't mean texting while driving or talking while driving and so on. It needs to be interfaced to you. So the human-machine interface is a very core competence in this field, speech and graphics, for instance. But let me show you a very short movie. It's a nice movie describing also the challenges which we are facing right now. And maybe this is an example how it could look like in 2030. But you will listen to the boy and his father discussing some of these topics. Can you check the output?
What is it you're counting?
My steps. What else could I be counting? What's the biggest number you know?
That's quite a question. Shall we sit down over there?
Okay.
Look at that Volkswagen. That was the very first car I owned.
And that was really your own car?
Small but mine. And had great mileage.
What do you mean?
Well, petrol. All cars used to use petrol.
Wow, so you were super rich then.
I wish, yeah. Petrol wasn't expensive back then.
And did you drive around in your car all day?
Of course not. Would have been much too exhausting.
You wanted to be reminded at 3 p.m. Please select a car you want to be picked up with.
So what did you do with the car when you didn't drive it?
It was just parked.
And then what?
That was it. You'd park it and pick it up again later.
And how did your car find you?
They didn't. I had to find my car instead. I kept in mind where I parked at night and went back the next day.
Sounds really complicated. And was it possible back then to dog onto your friends' cars?
Once I crashed into your mom's car in a traffic jam. But at least we met that way.
You were in a real traffic jam?
Not just once. Sometimes we got stuck in them for hours.
You have not yet selected a car. I can pick one for you if you like.
I picked the car today, okay?
Okay.
And you really crashed into Mom's car?
Be glad I did, or else you wouldn't be here today. So have you made a choice?
Yep.
Your car is on its way.
Hey, wow.
Sport.
So that's obviously a very nice way describing the future, how it could look like in 2028. That's the vision of Volkswagen Group Research. And of course, we can identify a few of these main problems which have to be resolved meanwhile. I'd like to talk about driver assistance, and then I'd like to go into the connected car, human-machine interface, and talk at the end about the mobility development. Driver assistance topics. So the driver as uncertainty factor causes of fatal accidents. If you look into the statistics here, you have 38% mental factors for fatal accidents. Incorrect decisions, 46%. That means 84% is misjudgment by the driver. I assume with hot chips, you are creating continuously great chips and computers, and you would not accept, of course, that the user would create so many problems, but as we know all, the user is usually the reason for the problems with the computers, and that's obviously also the same with the cars. What can we do to help? Vehicle safety, accidents over time. If you look into this very periodical figure here behind me, you can see it's a decrease, which is positive, right? But if you count 5,000 fatalities per year in Germany, and over 10 years, then you're counting pretty soon 50,000 people. So there's something which is really crazy, and I think someone compared it with an airplane crash. Would we accept that 2 airplanes would crash per day over the year? No, we would not accept that. But obviously, we are accepting that in our daily traffic experience. But what can we do? fatal accidents over time in Germany, obviously with the comparison of road fatalities in 1970 and today's, something changed. Billion person kilometers annually increased dramatically, so we were obviously able to find some technology to support, to help the driver to reduce the extreme out of his accident. What are these features? We are talking about vehicle safety. Of course, you know all these passive safety equipments. We have seat belts, crash zones, we have passenger compartments. Meanwhile, we have 13 airbags or more. Then we thought, okay, ABS, anti-blocking system or braking system, electronic stability program, and so on and so on. Obviously, these were good solutions for resolving the problem, which I just described. But what else is possible and where we are today? Effectivity of our current assistant and safety features. If you look into this graph here, you see fatal accidents, 100% was defined in the year 2000. We are today in 2010. So approximately that was a European Union target, reduction by 50%. What comes next? 50% is still, as mentioned, 5,000 people. We have the opportunity optimizing emergency medical response and so on, but what's the potential? And of course we have somehow noise here, so we have no chance to reduce this. That's beyond our control. Imagine you take the safety concept of our current Golf platform and just distribute that very consequently into the market. You would be able, through the additional passive and active safety systems, to reduce additionally these fatalities by approximately 25%. How do we calculate that? How do we find this figure? Of course, it needs a lot of research. We are working on the accident research, continuously investigating reasons for accidents to understand how can we protect, how can we optimize, how can we improve our technology. This is quite nice. Special effects through incentive programs means we introduce sooner newer technology, and that gives us also the potential to reduce accidents, fatal accidents. And if you look into active advanced driver systems like adaptive cruise control, like lane departure warning, like blind spot control or blind spot detection, you even have an additional 20% potential to reduce the fatalities as soon as possible. So that's quite interesting. And it's, of course, the potential behind that and the motivation to spend some money on the research to understand how can we actually optimize advanced driver assistance systems, for instance. Let me talk about the increasing need for safety. What is the reason that 84%, remember the figure at the beginning, 84% obviously tend to make a wrong decision? Well, let's separate the driving mode into two different modes. Under challenging the driver, it's really boring. You're just in the traffic jam, and over challenging the driver. It's extremely dangerous. And imagine, depending, of course, on the age of the driver itself. So if I imagine my kids would drive with a car, I'm sure that they're continuously over challenged, and they have to go through this curve of experience in their lives to understand how many dangerous situations do they have to experience to collect experience, to understand experience, and to become a good driver. Is that really necessary that we spend so much time on collecting experience to become a better driver, or can we actually create some assistance systems to support both situations? It would be great actually to have an autopilot button in the traffic jam and read your news magazine. And on the other hand, it would be perfect to have a rally driver like Walter Röhrl while you're over-challenged, and maybe he finds exactly the emergency path in the critical situation on the highway. So what do we need? We have two customer demands. In critical situations, we need driver assistance. The driver needs assistance, a safety angel. And in annoying situations, the driver wants assistance, so the autopilot. Of course, it depends on the mood, it depends on the situation, it depends on so many additional informations, but let's separate in between these two. What do we have so far installed in our cars? And you could, maybe you don't believe that it's already at this point of technology, but what we already implemented in many of our cars are multi-beam lasers, interior sensors, short-range radar, rear cameras, supersonic, a video camera, infrared camera, and so on and so on. Because we found there are so many opportunities to understand the environment, to understand exactly what's going up around you, what's going on around you, and you need to calculate that, you need to understand that, and you need to assist in these situations the driver. Very famous what we did so far together with Sebastian Thrun's office. He's the head of the Institute for Artificial Intelligence here at the Computer Science Center at Stanford. That was, we started in 2005 to create autonomous cars because we wanted to understand and separate in between the human driver and the machine. So we need to learn how to drive a car without a human. We started 2005 in the desert and we won the first DARPA Grand Challenge. In 2007 we continued with our junior. The challenge was a little bit different. We looked into the urban environment and understood that it needs an intersection algorithm, it needs some more. We needed to implement actually the Californian driving rules into junior. So if you ask, is it future story which you're telling us? No, it's not. We are looking into some of the applications coming pretty soon into the product. A traffic jam assistant, for instance, automatic parking. We have park assists already introduced and collision avoidance. It's an emergency brake system which breaks down automatically if it recognizes an obstacle within a specific speed range. Autonomy, maybe in 2020. Step by step, definitely we'd like to accomplish what's in the air. We'd like to find smartest solutions, but the customer, of course, needs to be willing to pay for the solutions at the end of the day. But from the research perspective, let me tell you that we're looking into building blocks of technology. We are separating in between driving at the limits of physics to understand how to lay out all the body and chassis components. Driving in unknown terrain, which is very interesting, and that was more done by Stanley, driving through the Mojave Desert, and driving according to traffic regulations. And even expanding the horizon of the driver through car2x. That's a communication in between the cars. Because you can suddenly look around the curve that someone is having an emergency situation and the cars can communicate and the driver can be warned. So predict danger. So the intelligent car, that's something we are working on, specifically here right now on the Pikes Peak TTS, where we wanted to implement through the algorithms a very famous rally driver, Walter Röhrl, who drove uphill the Pikes Peak a few 10 years ago. And we wanted to understand with this challenge, what is the extreme? What are the limits which we have to reach with our technology? This project is being done together with Chris Gerdes' lab. That's a driving dynamic lab here at Stanford, and we are really proud that we're going to drive uphill pretty soon in fall this year. So where's this project located? That's at the Volkswagen Automotive Innovation Lab, Vail at Stanford University. Let me show you, give me just an impression how it's going to look like. It's not driving very slow. Actually, we have a safety driver in this case here. It's going to make this dust. We are going to drive almost close to the race speed. We're really excited to continue working together with Stanford in this case. So what do we like to understand? Again, driving up to the limits. We need to reach the boundaries of physics, we need to understand what's necessary in the extreme situation to handle the car in the right way. An alternative is another video which I'd like to show you here. Imagine you're at the Fisherman's Wharf parking garage. Usually I have the kids with me and they're really annoyed by waiting. And you need to drive up to the 5th floor. Finally, you can find a parking spot. It takes you at least 25 minutes, at least. So wouldn't it be great just to press the button of your iPhone application, tell your car, find your parking spot yourself, drive up the parking garage, I go shop already. And that's what we did here in this little example. That was a demonstration which we had for last year for the driving event at Valet inauguration. And you can see it's finding its parking spot itself. It parks itself backwards. And the amazing part is, unfortunately I haven't found the video on YouTube, but there was a father and his son and they were talking and the father was so excited. See, that's really Ghost Driver. So I think that's something, obviously we don't need the steering wheel anymore because you see that turning. Of course, again, that's just an application looking into the future, but imagine there are alternative applications like valet charging. So you could drive your car, electrical car, maybe to the next charging station itself while you're working. So there are many applications and we're looking really seriously into these applications. Let me look into the car-to-car communication in the past. So that's a while ago. I assume I wasn't born at that time. I don't know, but that's, of course, the way of getting measurement data directly from the car driving in front. Fortunately, that changed a little bit. So there's definitely also progress in the car industry. What are the potentials of car-to-car communication? I'd like to continue to argue, of course, into the direction of safety. We have better safety due to early perception of critical situations. That's definitely possible. We have a higher efficiency due to up-to-date, precise traffic information, which is available. And a lively experience by vehicle-specific portal services and internet communities. Of course, safety, services, bring that together to really make driving also more enjoyable, but also, of course, more safe. Improving traffic safety. So that means we can communicate in between the ambulance and the driving car. We can create this in-car warning from traffic signs, a bad visibility. We have, of course, lots of solutions or roadworks can be one. The intersection assistance is quite interesting. You see how many accidents actually happen still at the intersection because someone oversaw a red light. Just stop the car with a red light. You can communicate directly with your engine control unit and you can stop that. Or you can communicate and warn another car which is approaching too fast that something is going to happen. So detecting opposing traffic, detecting crossing traffic and so on. So there are many opportunities. I'd like to talk about this car-to-X expanding the horizon again. So see these two Audis driving very close together and he's getting the information. Now there was something going on. There's a car actually stopped behind the curve. This one doesn't have connectivity on board. This one does. So and it follows, gets the warning into the cockpit, it drives around the curve, and that's exactly what we mean. You can avoid that. That's a very dangerous thing, and the other car knew already without seeing. So expanding the horizon of the driver. You might ask immediately, okay, if this technology is going to be introduced into the market, what does it mean? How many cars do we need? What's the market penetration for that to increase the safety effects? And you can see that in this graph, it means at least to have some effect, you need to wait a few years. You need to have lots of cars actually delivered with these kinds of technology, and it takes some time. But I'd like to encourage you, especially as experts for network, for computers, for routers and so on. This is a nice topic to collaborate. This is a nice topic, actually. Why don't we have a perfect testbed here in the Silicon Valley? This is so typical Silicon Valley technology, and I'd like to encourage you to work together here. Another nice example is find your parking lot fast, and I think we've already found many iPhone applications. Of course, how can you communicate with your car? The vision is in heterogeneous network. You have to have a very secure network for the safety features and a standard wireless LAN communicating, getting services and so on. So that is the connected car and the connected world. I'd like to continue with the human-machine interfaces. And here I also wanted to highlight very strong collaboration with Stanford, with Cliff Ness. He's an expert on human-machine interfaces. And of course we thought, if you have an autonomous car driving through the traffic, do you trust your car? Do you really press the autopilot button, let the car drive you through, I don't know, with 60 miles per hour? What kind of interfaces are required to adapt this new technology to you? And we had a very interesting study. We had created a car with a second steering wheel in the rear, and the driver couldn't see that. He pressed, or she pressed, the autopilot button and thought the machine would really drive without human help. Someone drove in the rear seat without being recognized by her and him. But you couldn't imagine, after a few seconds, they already took the newspaper and read the newest articles. So they trusted already the machine, which is great, somehow. And of course, we also initialized some emergency situations, so please go back to your steering wheel and take over. We need some help from you. And they did it. They put the news magazine back and just controlled the critical situation. And what did they do? Immediately pressed the button and started again. So it was really amazing. So that's shocking somehow, right? But that means also this aspect of human-machine interfaces, this understanding of psychology, that's so important to create a perfect interface. And of course, we have the responsibility to integrate that well. Mobile devices in the car or other instruments which are so distracting while driving are really critical. But again, that's a very extreme example which I just gave you. So, human-machine interfaces. Look at this example. I think what is she doing? Yeah, that was just an example for the driving simulator. She was supposed, I don't know if you could see that. She was supposed to do something here at the gearbox. So she had her handy here over there, and I think she just received a text message. The next one, I think, no, that's exactly what I meant. Yeah. So she's doing something there. Did you realize that she even didn't hit anymore the brake pedal? She was so shocked and surprised, overwhelmed by this situation. This very simple situation. She found something here and recognized immediately there was an obstacle coming, and nothing happened. She would have crashed extremely strong into the obstacle. So that's of course why we have here also psychologists to understand the human behavior and to work on this human-machine interface. So that's definitely distracted driving, right? And I think the example before that was receiving a text message. So, future of human-machine interfaces, we have basic driving functions, which are standard, but we have a new challenge, this automatic driving, reliable assistance. Do you believe in your systems? We have adaptive cruise control, we have blind spot detection, we have lane departure warning, you have at least 3 or 4 switches to turn it on and off, and so on. That's obviously overwhelming. So we need to optimize these interfaces, and that's, of course, a big challenge. New systems, we're not used to hybrids, we are not used to electrical cars. What does it mean? How do they influence our daily driving life? This needs to be optimized, and this needs, of course, also the aspect from the basis, it's safety relevant. And infotainment units, Yes, we'd like to get eventually text messages into the car, but what is the smartest way? Is it per voice recognition? Is it per display? I don't think that it makes sense to show the text message there. Is it connected to Facebook? So what do you expect from your car, actually? And this needs to be filtered very well. What we recently did very successfully together was with NVIDIA and Google. We created the successor of the infotainment unit for an A8, where we integrated Google Earth into the infotainment unit. And of course, in a very smart way, because it's depending on speed, it's depending on the driver. And it's integrated in the car. That's what we mean, which is so important. If you have your mobile device on your lap, then it's critical, because you're getting so distracted immediately. That's very scary. So infotainment evolution, location-based services and social networks, what do you expect in your car? Sometimes I prefer actually motorbikes, because you can talk with your BlackBerry, you can chat by email, but there's definitely need to communicate in the right way, right? The expectation is definitely there. If you receive today an email, the expectation that you give the response is getting higher and higher. I think within 30 minutes or so, the response is expected. If not, you get a phone call and they are checking immediately what's going on. So how does it affect the car? And who is the competition? So is it a mobile device? Or can we integrate something? Do we have new technologies? Maybe this guy? Of course, this needs to be found out, and we are going to work on these roadmaps to integrate that very carefully with the knowledge of psychologists and so on. But there's really cool potential behind that. You can get so much additional information, not just the traffic information. You know the fuel prices, you know timetables, restaurants and hotels, tourist information, and current events. So wouldn't it be great to drive down to Los Angeles and to entertain continuously the kids on the rear seat to talk about the environment, the history of the towns, and so on? Of course. So it needs a very smart filter depending on the situation. But don't distract the driver. Eventually distract the passengers. Sometimes it's maybe necessary, especially with kids. But back to the graphics and NVIDIA in this case. Why do we need a brilliant graphic into your car? I think that's, first of all, the expectation of brilliant quality, but it gives you additional information which is required and available in the internet. The expectation, as explained, is already very high. You have all this information at home, at your office, wherever. How do you get that in the smartest way into the car with a very nice graphic? And that's what we did again in this A8 recently, which was launched. So driver information with backend services. So you have this mix of information and you need to filter that in a very smart way. That's what we are doing continuously. Although there are many questions, why don't we integrate applications? Why don't we integrate web services and so on? We have everything already available in our smartphones. But I showed you the examples about the human-machine interfaces. Be careful. That's really distracting, and it results in fatal accidents, which we'd like to avoid with driver assistance systems, right? So it closes the loop. The harmonization of worldwide ITS standards is mandatory, of course. We are working on these topics. We are also working on these topics because we believe that only integrated systems will provide an acceptable solution. You need intelligent vehicles. You need the communication between the cars, and we have created already many consortiums to work on this, and you need an efficient traffic management to guide, to help, to steer the traffic of the future. So this is, of course, another nice example, which might be not necessary. I'd like to come to the last chapter now, that's e-mobility. And of course, there's high interest, especially looking into the future. What's expected? CO2 emissions are too high. what kind of drivetrain solutions do we provide, and what kind of research topics are we working on. We have a great example here in the Silicon Valley who are pioneers on this electrical vehicle technology, and we really respect their pioneers' work. And obviously, they were also able to push a little bit forward to show what's possible in regards to the available capacity for energy storage and so on. But let me explain you eventually the view from Volkswagen. It's not that we never worked on this topic. That's not true. Obviously, we have a long history. And it's quite interesting how many different concepts were being built up and tried out, and also even quite successfully, even hybrids and so on. So there's a differentiation, of course, in between electrical vehicles and hybrid electrical vehicles. And we are going to launch pretty soon also electrical GoAs, for instance. But e-mobility started very soon, and if you look into the electric power and you look into the T1 bus here, 70 kilowatt is not really amazing at that time, but it was already something which was quite accessible. In 1991, we had the study of the Chico, and we had the City Stromer, and today we are talking about fuel cell. Electric power is, meanwhile, very high up, but the technology is quite complicated. So what kind of alternative solutions do we have for the e-mobility? While we're looking into these future technologies, we're looking into the downsizing of existing combustion engines. So reducing the number of cylinders, reducing the emissions. We recently launched a clean diesel product here in California, and the emission laws were amazingly strong. And finally, we hit the target, and we were successfully and got the permission also to introduce these cars back into the market, which is a huge accomplishment, because if you already have a fuel consumption lowered by 30%, then of course the effect to the CO2 is directly proportional or somehow. So we need to look into continuously into natural gas, crude oil, but also into the renewable fuel opportunities. And of course, very high up here, the Blue Emotion e-tron concept, on which we are also working here in the Silicon Valley, which is an Audi concept. It's a very sportive car. Of course, it allows us to research on extreme technology. But let us look into the CO2 and energy efficiency of powertrains. And if you look into this here, this is the CO2 emission, and this is the energy wheel to wheel. Sorry, missed the translation here. And we have today's diesel engineers, of course, diesel engines, with approximately 90 grams per kilometer. And if you look into electrical vehicles and just make this comparison somehow in a country which depends on the energy mix of the power plants in this country, you find out that with an electrical car, you even come higher than 90 grams per kilogram. So it's not a very simple black and white world, of course. You all know about that. We need to look in all of the alternatives, but it's not really bad where we are with combustion engines concerning the CO2 overall balance. There's, of course, highest potential concerning CO2 and energy efficiency depending on the energy generating process. So if you look into the wind energy, for instance, in 2020, that's obviously a high potential there. But if we continue with our energy mix, then it's really the question which energy or powertrain has really a big advantage on that side. We're talking continuously about fuel cells here, but even with hydrogen wind energy fuel cells, it's very interesting. And if you look into the hydrogen generation process today through the energy mix, then it's obviously not the most efficient process here. But we are really looking into the center of this figure. We are optimizing continuously combustion engines, and we think that they are becoming close to the same level of CO2 and energy efficiency compared to the poor electrical drivetrain. Energy cost, that's quite interesting because we're going to pay for that, right? What's the right energy resources? We have so many opportunities here: natural gas, coal, nuclear, biomass, wind energy, and water and photovoltaic. And obviously, we see some potential in many of these resources. The renewable wind energy is obviously becoming very interesting in the future. But we need to look into that, and obviously still the photovoltaic process is quite expensive, and we're of course looking into the semiconductor industry to help to find the right products pretty soon, to find the right materials, to find the smartest electronics as soon as possible to optimize and improve also this technology. So electrification, we're talking here about a process. We need to differentiate in between technology, which should be available in the mass product. I told you that we are downsizing the combustion engines, reducing the volume, reducing the number of cylinders and so on. And actually I was involved in 2000 in a so-called Lupo concept, which was already at that time a mass product in 2000, which had a fuel consumption of 3 liters per 100 kilometer, which was it's approximately 60 miles per gallon. So a diesel engine with 3 cylinders, a very, very interesting concept. Interesting that obviously the consumer was not too interested in buying that. Unfortunately, the interest was at that time not too high. But of course, we continued to develop this technology and this knowledge further. So we were able to optimize these combustion engines. Start-stop, recuperation, Touareg hybrid, Golf twin drive, and we are talking about the electrical vehicle. So step by step, technology by technology, what do we need for these cars? Combustion engines are quite simple. Electrical power is approximately 2 kilowatt. But here we are looking into the electrical vehicle. We'd like to get a driving range more than 100 kilometers. Looking into the urban environment, city cars are really interesting for electrification. Of course, the demand, especially from Asia and China, is coming extremely fast. So we need to find a solution quite soon. What kind of technology is available? This good old lead acid battery. Of course, lithium-ion technology is obviously the highest potential to get a good solution for this higher expectation concerning the driving range. Not too deep into the cell chemistry, but I wanted to explain you how interesting it is to find the right setup of parameters to identify also the right storage for that. So it's not just take a battery and recharge that. No, it's much more. We have, for instance, here the 100-meter runner. That's more for the hybrid. So we have a different cell. In this case, maybe the capacity is just 5 ampere hour. And controversial to that, the high energy density, you'd like to have a marathon runner in your car. So you have to optimize in between these parameters. It's one of the battery systems with automotive cells. So it's a very complex system, and it's so much electronics in there. So it's a perfect location to be here, also in the Silicon Valley, but to work on these topics. But what I'd like to explain also is that there's a great opportunity that we have to find out in this worldwide global network, as explained at the beginning of my speech. And we are in the contest and competition within internal teams to find out what technology is the best, and what technology is the best for performance vehicles, high volume production vehicles, and city vehicles. If you look into the market and cost of lithium-ion cells, we expect a huge decrease concerning the cost. If you look into the lithium-ion cells and into the change here, we don't expect too much. Eventually, in the consumer cells, we are going to see a decrease, approximately 200 euro per kilowatt hours. That's a break point by now. We expect, of course, from forecast automotive cells, which are going right now into the series production, there's a huge potential also to find out that these are reliable and also payable. So we need to be able to pay for that. And if you imagine the price for a battery package today is approximately $6,000, and we pay for the production of a combustion engine approximately $1,000. So, you know, and that of course increases the cost, and the incentives are very positive, which we get also from the government. It needs a huge push also concerning the technology to get the price down. And challenge concerning the charging time. It's incredibly great, this gasoline. You get so much energy immediately into your car. It's so difficult to get that through your cables. And the interesting part is, of course, and I think Fritz Prinz, whom I met recently, mentioned it's so great, the combustion engine. You don't have to carry the oxygen with you. It's available in the air, and you just leave the CO2 somehow behind you. You don't need to carry that with you. But that's a little bit different compared to alternative storage capacity. And this gives you an example in which direction we are looking to. So this is the concept golf, which I'd like to present briefly. It's approximately 27 kilowatt hours lithium-ion automotive cells, so-called automotive cells, which are integrated into our concept golf Blue Emotion. And recently our CEO has announced that we're going to launch a product like that in 2013, 2014. So that's the end of my presentation. Thank you very much for your attention. I really like to encourage you, especially when you're from the field, from technology and the chips industry, let's work together. We need CPUs who are really optimized in terms of power consumption, which are optimized to have a low power architecture. We have an internet networking system on board. We are using so many energy resources, usually based on your electronics. Let's work together. We've created this Center of Expertise at Stanford. It's supposed to be an open, transparent forum here at the Stanford campus. I'd like to invite you to work together on connectivity, on driver assistance systems, and on e-mobility. Yeah, again, thank you very much for your attention, and I'm happy to receive questions.
Thank you, Dr. Huhnke. We certainly enjoyed your presentation and overview of the different technologies that go into cars quite a lot. I would say the vast majority of this audience didn't know that half of the components that you touched are actually in cars today already. We have time for a few questions.
James Stringali, Rambus. It was nice to see a coupling of two of my favorite technologies, autos and electronics. But as we all know in the room in computer science, when you put a lot of computers together, there's a possibility that things can go wrong in the system itself, not necessarily due to external events. I'm talking about, you didn't mention anything in your presentation about the failover systems or redundancies or things that are needed to make sure people, when you put a computer system running with hundreds of horsepower behind it, that something doesn't go wrong and cause the system itself cause a problem.
Definitely, that's a key, and where we definitely also can learn, for instance, from airplane construction redundancy. That's one of the keys. How can you create redundancy? You need to go through the failure analysis. What we are doing, for instance, for this autonomous hill climbing cars, we integrated a Java platform from Oracle, with whom we are collaborating on this topic, plus an additional platform from the Institute, and we combine both signals. Robustness of electronics, that's a key. Sometimes you have failures in devices, in little integrated circuits. You have software bugs. How can you reduce, of course, the failure rate? And that's a key, which needs to be researched continuously.
There one more aspect. With the wireless and the connectivity, there's also the possibility of malicious interference in the systems from external agents. There's been some great work down at UC San Diego, I believe, in this area, and I'm wondering if that's an area of research that you're also looking at.
So I really want to sit together with experts like you. Obviously, you are one. The question is, let's say, autonomous driving is one example. If you have interference with wireless networks and so on, you need, how do you need to change the infrastructure? Do you need reference points? Like in San Diego, we have this reference points, magnets integrated into the road to synchronize the systems again. We have, of course, many opportunities to optimize these channels, but the interesting part is to sit together to find out how to optimize, of course, also the systems and to face the problems of these technologies together.
Pete Stevenson, Stanford University. I thought the slide showing grams per kilometer and kilowatt hours per kilometer was very interesting. I don't know if you can go back. But one question that always bothers me when these issues come up is where do you draw the boundaries? And in particular, I saw this 2 different dots on there for hydrogen. One was on the inefficient corner and one was on the highly efficient corner. I don't know how to interpret that. Do you include the cost of producing the hydrogen?
Yeah, that's exactly the way. How do you generate hydrogen? Of course, you can use sun power, you can use wind power, but you can also use the energy mix, which we also saw. And if you generate hydrogen, it's nice, but not through this second loop of using fossil fuels to generate hydrogen. So that's a reason of how to generate the resources or how to generate the hydrogen.
So if I want to take that slide to settle some argument, say, where do I point? I say hydrogen is worse because it's in the inefficient quadrant, or I'm still, I guess, and the response to that would also be, did you draw the box around the cost of getting the oil out of the ground?
You mean this one here?
Yes.
Yeah, and that's energy mix today. So that's really the question, what do you take as a basis? If you use electrical energy to convert or to generate hydrogen, that's maybe not the smartest way. Or you take the energy from renewable resources like wind energy, or here in this case, wind energy, hydrogen, or solar power.
And does the gasoline dot include the cost of getting the oil out of the ground?
Can you repeat the question?
Do the dots for gasoline include the hydrogen dot includes the cost of getting the hydrogen?
Yeah.
Does the gasoline
it's included.
dot?
Yeah.
It's
of course,
all,
it's
okay.
an estimate, but it's approximately it's the overall balance which you're asking for. Mm-hmm.
Excellent. Very nice slide.
Mm-hmm.
Hi, Todd Besnick, Quantum. I was surprised that one thing didn't come up in your slides. That's something that I've seen discussed currently, is the ability to eliminate the slinky effect that we get when we get high density traffic. Do you understand what I'm talking about?
Which effect do you
The
mean?
slinky effect. So when people encounter traffic in front of them, they tend to slow down more than they really need to.
Yeah.
And this causes a traffic jam that stops, and then suddenly you're allowed to go 60 miles an hour, 80 kilometers per hour, and then you end up slowing down again. And it's not because the throughput of the roadway has been lowered, it's because of the way we drive.
Yeah.
So we can fix this, right?
There's one individual solution which is called adaptive cruise control to keep a constant distance, but it's very
But we don't have enough cars on the road, right? And here we are in Silicon Valley where we could get a bunch of commuters together to agree to put a device in their car.
Platooning concept, for instance.
Yes,
Yeah,
and we could do that tomorrow.
Okay, let's sit together. Let's do it. I definitely agree that this is a concept which was invented many, many years ago to optimize the air resistance and everything. So you definitely can reduce the fuel consumption for everyone. But of course, to find smart, logical processes to bring platoons together and leave them, this is eventually required. But yes, you're welcome. Let's work on that.
Ilya Gansov, Acronic Semiconductor. You showed a very interesting slide where the cost of batteries kind of going down with time. I'm just curious, what fraction of the cost of the car is the battery? And related to that, how much semiconductors contribute to the cost nowadays?
I gave you this example of approximately $6,000 per car right now compared to $1,000 per combustion engine right now. So that's factor 6 approximately to the existing technology. Of course, now you can talk about the rest, gearbox and so on, where you save some money. But that's a huge factor right now. So that's a problem why not everyone is ready to introduce immediately a mass product to the market. No one is willing to pay for that. And your second question?
Semiconductors, how much do they contribute and how do you see it in the future?
Definitely what we did so far was we created a low power architecture for the car. And if you imagine, I told you 50 processing units installed on board. That means you definitely have potential to reduce energy. But the more interesting part is, of course, the control and monitoring algorithms for battery monitoring systems, for driving prediction calculation and so on. So I see some more opportunity on the consumption side, but plus also on the intelligence side of making these systems smarter and more reliable.
Thanks.
Mm-hmm.
Thank you, Dr. Huhnke. Thanks for your time. Thanks for joining us at Hot Chips. We